Thought we'd take a look at the second fundamental theorem of calculus today. And so a lot of the second fundamental theorem, we're going to start with a function being defined as an integral. And I want to start with using these specific um, integrands or the terms inside of the integral. So let's look at problem number one. So we're going to look at capital F of x as the integral from 1 to x of 4t minus t squared dt. Okay, so let's take the antiderivative and then we're going to plug in our bounds. So that gives me f of x equals, now the antiderivative of 4t would be 2t squared minus the antiderivative of t squared would be 1/3 t cubed, and we're going from 1 to x. Now, using the first fundamental theorem, now we can plug in our bounds. We'll start with the top bound of x, and then we'll subtract and plug in the second bound of 1. So that gives me 2 minus 1/3. And that sees we ends up with f of x minus 1/3 x cubed. Excuse me, let me fix that. Minus 2 minus 1/3 is 5/3. Okay. Now, let's turn around and find the derivative of that. Okay, so we'll take the derivative, and that gives me 4x minus 1/3 times 3 gives me x squared, and then the derivative of a constant is 0. Look at the connection here. Look at what we started with. Took the antiderivative, then we took the derivative, and looks very similar. Okay, let's keep going. Okay, this time we'll let cosine be on the inside. And again, we'll take the antiderivative. So antiderivative of cosine is sine. And now we'll plug in the bounds. So we get sine of x minus sine of 1, which sine of 1 we could put in a calculator and get a value. Now, take the derivative. The derivative of sine is cosine, and the derivative of sine of 1, because it's a number, is 0. Interesting. Again, notice the connection here. Okay, look at number 3 now. We're going to define the integral now from 1 to x squared. Let's see if it makes a difference here. So capital F of x is the integral from 1 to x squared of t cubed here in number 3. Again, let's take the antiderivative. The antiderivative of t cubed would be 1/4 t to the 4th. And we have our bound. Oops, our bounds are x squared. There we go. So now let's plug in our bounds. I've got 1/4 times x squared to the 4th minus 1/4. We plug in 1, right? So that gives me 1/4 x to the 8th. Think about when we raise a power to a power, we multiply the powers. And now let's take the derivative. So I've got 1/4 times 8, which gives me 2x to the 7th. Okay, so this time we didn't get the same on the inside. So that must be a difference we're going to have to account for. Okay, let's do one more. This one we're letting capital F of x be the integral from 1 to x squared of 6 square root of t dt. So we'll take the antiderivative. The antiderivative of 6t to the 1/2 would be 6t to the 3/2 over 3/2. And again, we're going from 1 to x squared. Okay, let's clean that up just a little bit. Let's see, that's going to be 2/3 in front times 6. And then I've got square root of t and being cubed. And we're going from 1 to x squared. Okay, so that gives me, if I plug in my bounds, here I'll have 4. Square root of x squared will be x, so I've got x cubed minus 4. and then take the derivative of that, and I get 12x squared. Again, different, okay? So when the upper bound was just an x, we got the exact same on the inside. When the upper bound was an x squared, we got something different on the than what was on the inside. So there must be a connection between the two. Something else must be going on here. And there is. It's the second fundamental theorem. So, which says if capital F of x equals the integral from a number to a function g of x of f of t dt, where a is any number, or maybe we say where a is any constant, then capital F of prime of x will equal f of g of x times g prime of x. Okay, so we did the antiderivative. We already did the approach here. We found capital F to be 4x minus x squared. We did that before. Now, if we do the same approach here, so we make sure that bottom bound is a constant, we can substitute in the upper bound here. When we take the derivative, we just get 4x minus x squared. See, the derivative and the integral will cancel each other out, but we will substitute in the x here instead of the t. For the next one, we found this one to be f prime of x was cosine x. We did that just in the problem before. Now, when we do it over here, notice we take the upper bound, because that lower bound's a constant, take that upper bound, substitute it in for the variable, and again, we get cosine x. Now, where this gets interesting is at the bottom, because remember, these were the two that we did not get them to agree. So this one was where we got capital F of x was 2x to the 7th. Let's see how that actually plays out here. If I do the fundamental theorem here, I'm going to substitute in x squared for t. So that's where I get x squared to the 3rd. And then I've got to multiply by the derivative of the bound. So the derivative of x squared is 2x. So this is how I get x to the 6th times x. That gives me x to the 7th, and then I have a 2 in front. So I get the same answer when I do the second fundamental theorem, but we didn't know why before now. So remember when we did this problem, we got 12x squared as our derivative. Let's try it with the second fundamental theorem. We take the bound here and we substitute it in for t. Then we multiply by the derivative of the bound. So the derivative of x squared is 2x. And this is why we get 6 times 2 is 12. Then I get the square root of x squared, which is x, times x gives me the x squared. And that's how the second fundamental theorem really impacts, because it allows you to do all of that just by substituting in the bound, whether you actually can take the antiderivative or not. Because what we're going to find is that sometimes we have to deal with functions where we cannot find the antiderivative. Okay, so let's look at these, okay? Notice here, I actually could take the antiderivative, but maybe if I'm in a calculus AB, this is not a skill and integration technique we learn. So we have to use the fundamental theorem. Remember, you're going to substitute the bound in first. Make sure your upper bound has the variable and your lower bound is a constant. Then you can substitute. So you'll have 2 minus 2x squared. And then you're going to multiply by the derivative of the 2x, which is 2. Now, if you clean that up, you're going to get 2 minus 4x squared times 2, or you can put the 2 in front of the square root like that. Okay, now we have a problem here in the second one. And our problem is that the function in the bounds is on the bottom. So the only way to get it to the top is to make it negative. So you're going to rewrite it first. Because remember, the fundamental theorem only works, second fundamental theorem only works if that bottom bound is a constant, the upper bound is a function. Okay, now if we want the derivative, then I've got the negative. Let's substitute our bound in for the variable. So I've got negative e to the cosine of x squared. And then I've got to be sure and multiply by the derivative of the bound here, which is 2x. So my g prime of x equals negative 2x e to the cosine of x squared. All right, one more like this before we start looking at some free response questions. Notice in this one, we do have the bound on the top. So we're going to take the derivative simply by substituting in the bound. That'll give me cosine squared, cosine x squared. And then I'm going to multiply by the derivative of the bound. The derivative of cosine is negative sine. And so my derivative becomes negative cosine squared sine. So feel free to use that shortcut. It's really going to help you quite a bit. Now let's put this together in some free response questions. So you're given the graph of g of t. But notice then how f of x is defined. So depending on what we're looking for, we will use g of t sparingly. Okay, so we're asked to find f of 0. So f of 0 is going to be defined as the integral from negative 4 to 2 times 0 of g of t. So this is the integral from negative 4 to 0 of g of t. That means on this graph, we're going to go find the area from negative 4 to 0. So from negative 4, we've got this area and this area and all of this area. Okay? So notice the two triangles at the beginning cancel each other out. One's below the x-axis, one's above the x-axis. Then we have this rectangle that I'm probably going to use that I can calculate. That's a 2 by 1 rectangle. So I know the area is going to be 2 times 1. Then I've got a quarter circle. So I've got a quarter circle up in this upper region here, and it has a radius of 2. So I'm going to add that too. So a quarter circle is 1/4 pi. Your radius is 2, so we'll square that. And so f of 0 actually gives me 2 plus, and then 2 squared is 4, times a quarter is 1 pi. So f of 0 is 2 plus pi. And I did all of that from the integral equation, but then I had to translate the integral to the area. Okay, let's look at number 2. Number 2 says find f of 2. Okay, so if we're doing f of 2, that's the integral from negative 4 to 2 times 2 of g of t dt. So that's the integral from negative 4 to 4 of g of t dt. Now, I'm one that wants to save as much effort as we can. So I want you to notice we already calculated the integral from negative 4 to 0. So it's probably in our best interest to go and get that area from negative 4 to 0 and then add to it an area from 0 to 4. Now, if you look at this graph though, do you notice the symmetry? Do you see that there's y-axis symmetry going on? That the area over here is identical to the area over here? So really, I could double the area from negative 4 to 0 to get my total area for f of 2, which in this case would be 2 times 2 plus pi. Friends, you want to work smarter, not harder on this. Definitely watch all of the details, okay? Now, number 3, we want to find now the derivative. So let's go to our equation and find our derivative of f. Check yourself. see if the constant's in the lower bound, see if the function is in the upper bound. In this case, it is. So we can do a substitution. So we'll get g of 2x times derivative of the upper bound, which is 2. Now plug in 1. Okay, so f prime of 1 will be 2 times g of 2 times 1, which is 2. Now remember, g of 2 is your y value at 2. So your y value at 2 is actually 1. And so you get the derivative at 1 is 2. Now, look at number 4 then. We want to find the derivative at negative 2. So we're going to come back and get our same derivative equation we've already done. Tells us that the derivative of f of x is 2 times g of 2x, and we can plug in negative 2 now. So 2 times negative 2 gives me negative 4. Now you're going to have to go on the graph and find g of negative 4. So your y value at negative 4 is negative 1. So f prime of negative 2 equals negative 2. Okay, now the last one from this graph is we're looking for f double prime of 2, but we need to find f prime. I'm sorry, we have f prime. We need to find f double prime. So f double prime of x is going to be 2 times chain rule here. G prime of 2x times derivative of 2x, which is 2. So we get that the f double prime is 4 times g prime of 2x. Now we can plug in 2 for x. So f double prime of 2 would be 4 times g prime of 2 times 2, which is 4. Now, when you go on this graph, g prime is the slope. So the slope at 4, you're going to look here. You're going to calculate the rise over the run. But what about the fact that it stops there? What about, do we have a derivative there if the graph stops? We don't. So that means that f double prime of 2 does not exist because g prime of 4, whoops, does not exist. So remember, we can't have a derivative if you're at an endpoint of a graph. So I hope that helps. We've got just a few more to look at here. So this one would say, given to the right function of f of t, 3 line segments in a semicircle. Look at how g of x is defined. And let's start. So we're going to plug in, looks like we want g of negative 6. So g of negative 6, we're going to have the bounds from negative 1 to negative 6. Now, friends, those bounds are backwards. So in order to calculate our area, we've got to put a negative in front. We've got to go from negative 6 to negative 1. And then let's go to the graph and find that area. So from negative 6, I've got this area. Then I've got this area here. So it looks like a triangle and a trapezoid. Notice the trapezoid is below the x-axis. We will have to account for that. Let's do the triangle first. So I've got 1/2 times the base, which is 2, times the height, which is 4. Now I'm going to subtract so I can do the trapezoid. That's 1/2 times the height, which is 2. And then we add the bases. So let's see, this base is 1, 2, 3. And this base is 1, 2. So it looks like I've got 4. And then I've got minus 5. So g of negative 6 is negative 1. Now let's find g of 6. So this will be the area from negative 1 to 6 of your graph. And so let's see, we've got negative 1 to 6. So that looks like a trapezoid. Oops, and a quarter circle we're going to be working with there. So let's do the trapezoid. Notice it is below the x-axis. I do have to account for that. So I've got negative 1/2 times the height of my trapezoid, which is 2. And then I'm going to add the bases. Let's see, this is 1, 2, 3, and 1, 2, 3, 4, 5. Okay, then let's add our quarter circle. So that's 1/4 pi. And my radius here looks to be 2. So we'll square that. All right, so it looks like we've got a negative half times 2 is 1, 8. So we got negative 8 plus 4 times a fourth. So negative 8 plus pi there. Okay, number 3 then, we find the derivative. Let's find the derivative of our equation there. So the derivative of g of x looks like the constant's on the bottom. The function is in the top bound. So we're good to use second fundamental theorem. We'll go ahead and substitute. Looks like g prime is equal to f of x. So when I'm looking for g prime of 6, I'm really looking for f of 6. That means go on the graph, find the y value at 6. The y value at 6 is 2. Okay, look at number 4 then. I'm looking for g prime of 2 here, which really is the same as f of 2. So I'm going on my graph. F of 2 is the y value at 2, and that looks to be negative 2. All right. Now, the second two ask us about g double prime. So we're going to take the derivative of this equation. So that gives me g double prime of x is equal to f prime of x. F prime of x is the slope of this graph. So when we ask for g double prime of 2, we're asking for what is the slope of this graph at 2. The slope of this graph at 2 does not exist because there is a sharp turn. Okay. Now the last one, let's see. G double prime of negative 4 would be f prime of negative 4. That means go on this graph and tell me the slope at negative 4. So the slope there is a line segment. You can calculate the rise over run. So it looks like it's down 6, run 3. So it looks like I'm going to get 6 over negative 3, which is negative 2, because that is the slope of this graph. So we're moving quickly through some of these problems, but you're getting the idea. I want you to see a lot of different approaches to it, because it is one we see often on free response. We're given a function f consists of 2 quarter circles. So that's important to know that they told you that in words. This is a quarter circle, even though it might not look like it. And this is a quarter circle, and then one line segment. And you're told g of x, look how g of x is defined. A little bit different, okay? So when you want to find g of 3, we plug in 3 for x. So that gives me 1/2 times 3 squared plus the integral from 0 to 3 of f of t. Okay, so g of 3 would be 9/2, and now we've got to go get the area. Okay, so we've got this area, and we've got this area, and I'm not 100% sure they're exactly the same, but we can check it out. What would the equation of this line be here? Well, it looks like it has a point there. It's got a point, it's a line segment at 3, negative 3. Looks like it hits the y-axis there at 3. So the slope there is down 6, run 3. So it looks like this segment is y equals negative 2x plus 3. So it's going to hit the x-axis at 1.5. which is going to give this area above the x-axis to be the same as this area below. And so that's going to give us a net area of 0. So that means my g of 3 is 9/2. Let's do one more like that. We'll plug in -4. So I've got -4 for x. Now notice when I do this that my bounds are backwards, so I'm going to have to deal with that. -4 squared is 16 times 1/2 is 8. Now switch your bounds by putting a negative in front. And then let's do the area from -4 to 0. Remember, these are the quarter circles, and we've got a negative in front. So I'm going to do the first one, which is negative. So I got -1/4 pi, and then my radius looks to be 1. Okay. Then I've got this quarter circle above the x-axis, so that's a 1/4 pi, and the radius here is 3. So all we got to do is clean this up just a bit. So I've got 8 plus 1/4 pi. I'm distributing the negative, minus 9/4 pi. That's going to give me -8/4 pi, which is -2. So I get that 8 minus 2 pi is g of -4. All right, 2 more. Let's see. Now the next one, we're going to need g prime. So we take the derivative of g. So g prime, take the derivative like normal of this 1/2 x squared. That gives you x plus, now do your substitution, f of x. Now you can plug in 3. So g prime of 3 would be 3 plus f of 3. Remember what f of 3 means. Go on the graph, find the y value when x is 3, and you get -3. So g prime of 3 is actually 0. Don't be worried about the answer being 0. It's a perfectly acceptable answer. All right, now let's find g double prime. We have g prime, so take the derivative here. G double prime would be the derivative of x, which is 1, plus the derivative of f of x, which is f prime. So now you can plug in 2. Now, f prime of 2 means to go find the slope on this graph at 2. Okay, we found it earlier at, that gave us -2. So it looks like g double prime of 2 is -1. So friends, I hope this helps you with the second fundamental theorem. I hope you can see in these last few examples how some free response questions are going to be asked. As always, if you have questions or comments, be sure and leave them below. I'd be happy to help. Bye for now.